Hello and a very good morning to everyone. My name is Hafiz and I am an applications engineer here at National Instruments. Thank you for joining me this morning as we explore how we can increase system efficiency with condition monitoring. Let us begin the webcast with a simple analogy that most of us can relate to. If you own a car, you would understand that there are routine maintenance, which includes oil changes, tire alignments and other critical inspections. They are usually done based on the number of months or the number of kilometers traveled. But you may realize that you could be changing your oil too frequently or not frequently enough, especially if you drive in a dusty environment, causing a cascading effect on your engine. Thus, the best case scenario would be that you are able to confidently predict when to change the oil independent of time or conditions. Industries, they face a similar scenario when it comes to their equipment. Here in this webcast, we will look at how National Instruments help industries save costs as they move towards online monitoring and predictive maintenance. National Instruments has a long history of delivering products and solutions geared towards condition monitoring applications. Our team has been active in not only providing specialized quality condition monitoring hardware, but we have also developed software solutions such as the order analysis algorithms in the sound and vibration toolkit, and more recently the Insight CM Enterprise solution. This can be seen from the 300 over documented case studies in the use of our technology. These are some of the industrial partners that we have worked with to maximize the potential of our technology, including the Center for Intelligent Maintenance Systems, the National Institute for Renewable Energy, and the Vibration Institute, just to name a few. We also have a strong repertoire in various industrial applications that range from manufacturing, transportation to power generation. Let us take a look at the traditional maintenance strategies and how condition monitoring can improve them. There are 4 general maintenance techniques. Firstly, we have no maintenance or run to failure. You wouldn't think that this is a maintenance technique, but in some cases it is actually an okay scenario to let the machines run to failure. Often they are non-critical or inexpensive machinery. Secondly, periodic maintenance is the idea that the machine is simply brought offline on a routine basis and serviced. This can be quite expensive due to its high frequency and increased downtime. Maintenance personnel often are fixing perfectly good machines, and in the process of the routine maintenance can sometimes break the machine. Next, we have diagnostics, where the machine is being continuously monitored with online equipment with our compact Rio devices. This aids in the finding of failures before something catastrophic happens, but it is still an unexpected failure and causes significant downtime. However, the machine is probably saved. Lastly, prognostics is the idea of trying to predict when machines will fail. This can be done by monitoring several variables and calculating the remaining useful life. This allows maintenance personnel to schedule the appropriate times for repairs and reduces downtime. As mentioned earlier, several maintenance strategies exist. This diagram aims to show you the advantages of using predictive maintenance to maximize the runtime of your machine without the risk of running into a complete machine failure. As we look at condition monitoring, we see several sensory measurements which provide the view of the health of the machine. National Instruments offers a platform which incorporates hardware to make direct measurements from analog and digital sensors. We also provide solutions to communicate with control systems to simultaneously note the operational state of the machine being monitored. There are several sensory measurements to be made in condition monitoring. Vibrations are the most common and today offer the most information regarding the health of machine components. We can classify rotating machinery into two broad categories: ancillary or balance of plant type of equipment. These include boilers, pumps, gears, and so on. These type of machines almost always run at a steady state, and so periodic or event-based measurements are quite acceptable. Then there are high-value, critical to business operations type of equipment. Not only do these equipments require periodic measurements, but transient data during a coast up or rundown is just as important. A common plant asset where prognostics can be used is the electric motor-driven machine. Electric motor-driven machines include pumps, fans, blowers, and many other machines. This class of machines is the most commonly used machine in the world. Here at NI, we like to surprise people with the little known fact that there are more induction motors on planet Earth than there are actually people. Electrical motor machines are often driven by induction motors. Their rotating shafts are supported by roller element bearings. In addition, gearboxes provide speed changing mechanics, and fans and pumps have vanes and blades. To test or monitor an electrical machine, we may use several sensors. These include accelerometers for vibration, tachometers for speed, as well as pressure and cavitation sensors for blade or vane monitoring, and even electrical power sensors to monitor the motor itself. We conduct an FFT on the time domain waveform from these sensors, allowing us to monitor vibrations at different specific fault frequencies. As with any machine monitoring or test application, data logging at specific times or events creates a series of data files for offline analysis. With proper labeling of sensory data recordings, it is possible to conduct analysis across multiple files. In most cases, dynamic signal acquisition hardware with 24-bit resolution, simultaneous sampling, power for sensors, and anti-aliasing filters are desired. Now that we understand a little bit more about predictive maintenance, let us have a look at the business benefits of employing such a strategy. Previously, we have looked at the maintenance costs of maintaining a machine, but how about the production output lost due to downtime? Now, let us compare the production availability of a predictive-based strategy and a preventive maintenance or time-based maintenance approach. In a preventive time-based maintenance, the system repairs are carried out during times of low production level, even when not required by the machine's health. It can be a source of wasted energy and lost production time. Possibility of an unplanned or even worse, catastrophic machine failure can still occur before the manufacturer's recommended repair time. Predictive maintenance, on the other hand, is time agnostic and uses health monitoring to optimize resources. Problems are only fixed when needed, allowing for more machine production uptime and no unexpected failures. When we talk about increased revenue, we are increasing uptime. This means that you are producing more, and higher yield means higher revenue. It's also not about the machines being on or off. So it's also about making sure that they are running efficiently and at an optimal operating condition. Now, what about cost reduction? Well, if you don't do repairs when they are not necessary, you save money on parts and labor. We also look at optimizing the workforce by automating what was previously done manually. So not only can we gather more data, but also more minds can be focused on understanding the condition of the assets. Then there is also the benefit of reduced risk. Reducing repairs means reducing worker exposure to dangers. This is especially so for large machinery due to its dangerous nature at which it operates. Apart from that, there is a risk of machine failure occurring, resulting in lost revenue and unforeseen repair costs. This risk increases as installed machinery continues to age and the cost is higher with the increasing complexity of newer machines. The following pictures show how collateral damage from a part failure can rack up repair costs. In this example, a bent shaft caused the impeller to have contact with the casing and diffuser vanes, causing it to bend. Moreover, it caused damage to the gear teeth. In this example, a problematic bearing, when detected early, only costs $5,000 for a one-day repair. However, if left to run to failure, can cost upwards of about $150,000 for a multi-day repair. In this particular instance, the bearing seized up, came apart, and caused the expensive electrical motor trying to turn this shaft to burn up. As such, you can see how properly executed predictive maintenance activities, beginning with effective condition monitoring, can equip industries with the tools and the knowledge to minimize costs, realize efficiencies, and improve reliability. A research done by the Electrical Power Research Institute revealed that the comparative maintenance costs per horsepower for predictive maintenance is significantly lower. According to the research, scheduled maintenance strategy is the most expensive at $24 per horsepower. This is followed closely behind by a reactive maintenance strategy at $17 per horsepower. Finally, the research shows a cost-effective figure of only $9 per horsepower for predictive maintenance. As an example, this is how a distributed condition monitoring system can save the customers money. Based on a lifetime condition monitoring cost of $11,000, a 1 megawatt wind turbine would save $60,000 in repair costs over its lifetime. Apart from the end user, the OEM of these machines also benefit from such strategies, of which the most important is machine data. With available data on all products' performance, the OEM helps improve reliability metrics while also generating service revenue. With monitoring tools, the service team also collects data regarding operation in and out of warranty. The machine supplier, or OEM, can then use this data to improve the design of the machines. In addition, data collected from one machine can then be used to access other machines' health. This is a study done by the Aberdeen Group showing that taking the service work from a physical visit approach to a remote monitoring approach has significant financial benefits to the OEM. By implementing a distributed condition monitoring system, such as with a compact radio, they can reduce service calls by more than 30%. Now, let's explore how moving towards an online condition monitoring approach can benefit you. If we focus briefly on the condition monitoring market opportunity, there are multiple trends driving growth and the use of new technologies in this space. And looking at vibration alone, the condition monitoring equipment market is $1 billion and growing steadily. More and more companies are faced with reliability challenges amidst tightened profits, aging equipment, and complex repairs. These companies want to reduce the risk of failures, costs, and downtime incurred by unscheduled maintenance and increase their production, yield, and ultimately revenue. As an example, the current machine monitoring program at Duke essentially consists of a limited number of predictive maintenance specialists manually collecting data on their assets. Duke, a power generation company in the US, estimates that they manually collect about 60,000 vibration readings each month. The analysis shows that they are spending 80% of the time collecting data and only 20% doing analysis. Not only is that very time-consuming, Duke and the industry's experienced workforce is also approaching retirement age. At the same time, they are unable to backfill the positions as new college graduates are not interested in taking these jobs. Thus, they are left with reduced staffing, having to operate, monitor, and maintain the assets. With this, Duke's executives challenged them to use technology to address the increasing reliability demands and to better optimize their workforce. As discussed earlier, there are problems with the current way of conducting predictive maintenance. Necessity often brings ingenuity, and using an automated data collection and analysis solution helps to address these problems. Automating data collection frees up scarce vibration experts to cover more assets. This is further motivated by decreased costs in sensor and data acquisition hardware, allowing permanent installs. Adding to that, it also makes fusing diverse sensor data to get more accurate diagnosis more financially feasible. Big data with analytics also trigger the adoption of fleet-wide automated monitoring systems. Traditional maintenance is either regularly scheduled based on time intervals or occurs reactively once the machine has unexpectedly failed. Traditional diagnosis occurs by performing a route-based method utilizing disjoint systems, which is costly. The sensor integration is also limited to vibration, temperature, or other relatively simple process data. Instead, what the industry wants are intelligent, online integrated systems which can continually analyze data for degradation. They would also be able to make smart performance predictions as close to the sensor as possible in order to prevent failure. With all the points in mind, you can easily see how the promise of new data-driven businesses, greater transparency on how operations work, better predictions, and faster testing can be so alluring. Let us take a look at a case study to see how the points discussed earlier can affect a real example, its implications, and its solution. We will be looking at Duke Energy, a major power generation company in the US. As you can see, they have both a large fleet of assets as well as a high number of employees. Aging equipment and the closure of older coal plants requires the remaining plants to be more reliable. More modern technologies in energy production is also susceptible to catastrophic failures, leading to high costs. Maintenance specialist programs were inefficient and is made worse with its declining numbers. Thus, a solution to address these issues became pertinent to ensure success of the company. The situation was further exacerbated with an accident due to a major catastrophic failure. A transformer blew up, causing millions worth of damage. Monitoring the temperature on the connected transmission line could have prevented it. One or two of such events can easily justify the cost of a fleet-wide solution. With a smart monitoring program, Duke's current solution comprises of continuously monitoring 10,000 assets over 60 plants. With a fleet of about 30,000 sensors, they primarily look at vibration and then EMSA and thermal imaging. In their application, they are deploying nearly 2,000 compact Rio devices. Using online condition monitoring, they were able to modify the workflow as such. In the first step, a circulating water pump at Heinz plant has just been instrumented with a serial. Data is sent through the system, and when the M&D Center's advanced pattern recognition software detects a deviation or a change in behavior, it generates an alarm. An email is then generated and is received by the remote predictive maintenance specialist. The specialist simply opens his laptop, remotely logs in and views the data and recognizes the issue as a clogged intake valve. He or she is able to call the plant and schedule downtime and maintenance of this part. As a result, catastrophic failure is avoided through detection. The specialist did not have to travel to take measurements manually, and the issue was detected and diagnosed right away, avoiding unscheduled downtime. So, why did Duke choose NI? Well, they chose NI due to the open architecture that NI can provide. The solution was also more cost-effective, and we provided interoperability with other historian software. The simplicity of licensing was another factor that Duke favored heavily. We are thus proud to share our latest solution to online condition monitoring, which is InsightCM. It is targeted to help companies gain insight into the health of their capital equipment for machine maintenance and operations. It is also the first end-to-end software solution that addresses big analog data challenges and builds on the industrial Internet of Things. The NI InsightCM Enterprise pairs with a ready-to-run condition monitoring systems, which is the Compact Rio hardware platform to acquire from a wide range of sensors. This can help in improved fault diagnosis for maintenance specialists to analyze. It also aims to be a cost-effective solution for enterprises by lowering the instrumentation costs for monitoring equipment at a fleet-wide scale. Offering open software architecture allows interoperability with third-party enterprise software packages. Being easily scalable too, you can move from 1 to hundreds of nodes per InsightCM enterprise server and then simply replicate it at multiple facilities. Its flexibility allows Serial to adapt to changing sensory needs while maintaining the user's investment in the platform. The NI InsightCM Enterprise comprises of two main softwares, the server as well as the Data Explorer. The NI InsightCM Enterprise is a distributed online monitoring system with the InsightCM server as its core. It is a thin client used to configure and monitor the health of the acquisition devices. It also controls other aspects of the server, such as generating and monitoring configurable alarms, managing data, and controlling user access. In addition, it provides interoperability with third-party historian software such as CMMSs, database historians, and prognostic tools. The data it collects is then accessed by Data Explorer that provides data analytics and visualization remotely. You can then use Data Explorer to show and identify the trends of different frequency bands based on specific parts of the machine. Or you can use it to compute numerous analytic data such as trend plots, FFT, polar plots, and so on. You can even subscribe to near-live data of machines during a transient operation remotely. In short, the NI InsightCM Enterprise is a ready-to-run software solution with tightly integrated and flexible hardware options that not only acquires and analyzes measurements, but also generate alarms, allows users to visualize and manage data as well as results, simplifies remote management for large deployments of monitoring systems, and is also able to integrate with existing enterprise infrastructure and software packages. This online condition monitoring solution is ideal for companies in a variety of industries, including oil and gas, power generation, mining, rail, and industrial manufacturing that need to optimize machine performance, maximize uptime, and reduce costs, as well as increase safety. So it has always been our mission to empower engineers in emerging countries to achieve sustainable prosperity. We are thus committed to providing increased access to NI technology. As such, if you are located at any of the above countries, you may wish to contact your local representative and see if you are eligible for direct support, be able to work with local incubators, and collaborate with public sector partners. We hope to be able to nurture local innovations in your country. That is the end of the presentation, and I thank you once again for joining me on this journey. I hope this has enlightened you on how online condition monitoring can help your industry. And I hope that you will think about the advantages of employing predictive maintenance the next time you see a rotating machine. Do share your thoughts on this, and if you have any further queries, I would be very interested to know more about it in the short Q&A after this. Thank you.